In this chapter, we're going to be studying the gas laws, and in particular, how ideal gases might behave. So the first thing to understand is that there's no such thing as an ideal gas or ideal behavior, but we can model what an ideal gas might behave like, and that will help us understand how gases in general will behave. So part of those assumptions are here in the kinetic molecular theory of gases, and let's just go over them one by one. The first assumption is that gases are made up of small atoms or molecules that are in constant, random, and linear motion. What that really means is that any path is available for an atom or molecule to travel. In other words, there's nothing to prevent an ideal gas molecule from straying from its path. If it's on some particular path of motion, nothing is going to get in the way because as an ideal gas would behave, it is not influenced by anything else. It doesn't see any other molecules to be influenced by. It doesn't see any other forces to be influenced by. The second assumption is that the distance of separation is very large compared to the size of the individual atoms or molecules. That's another way of saying that the density is very low. So remember, the density is equal to the mass divided by the volume. And in this case, if the volume is very, very large compared to its mass, that means the density is low. If the density is low, that makes sense for the first assumption then, because that means that there's less chance of any particular molecule on a path to come across any other molecule on any other path for them to influence each other. It's mostly empty space. What that also means is that it's highly compressible. Now, the third assumption is that all gas particles behave independently. That means, ideally, there would be no attractive or repulsive forces between particles. Now, most of these assumptions are fairly reasonable. Molecules of gas particles are very, very far apart. In other words, the density is very low. There's mostly empty space in a volume of gas. So that means that assumption one is fairly reasonable. If a molecule is on a particular path, it's very unlikely to come across any other molecule on a different path for it to be influenced by. So 1 and 2 seem pretty reasonable. But assumption 3 is actually quite far from reality. In reality, and we've already seen this earlier in lecture, there are intermolecular attractive forces between molecules that are polar, which means that they need more energy to overcome those intermolecular attractive forces. So there's a departure between ideal behavior and how gases behave in reality. But there's some other things, part of number 3 here, that do make pretty good sense with what we see in nature. For example, part of this assumption is that gas molecules will expand to fill the available volume, and that they will readily diffuse through each other if there's more than one gas. For example, if I release some hydrogen gas from the lower left-hand corner of this slide, from this little container here in this box, what we'll find is that that hydrogen gas will now go and expand and fill up the entire space available as defined by the walls of the vessel. All right, so that's expanding to fill the available volume. Now, in the upper right-hand corner, let's say at the same time, we release some oxygen gas. Just like we found with the hydrogen gas, it will fill the available volume, but because of the earlier assumptions, each one is mostly empty space with respect to the volume it occupies relative to the mass of the molecules. So they are still traveling to fill the available space as if they're never going to see any other molecule along the way. Assumption 1, any path is available to travel and it's not deterred by running into anything else. So that's what I mean by they will readily diffuse through each other as if each was in isolation. Okay, now let's consider once again that with assumption 2, they occupy mostly empty space, and combine that with the idea that with intermolecular attractive forces, like if they're polar, for example, that you need to apply more energy to the molecules to get them to separate from each other, to get them to act more ideally. So if you consider both of those together, we can say the following, that a gas will behave most ideally at a low pressure because the lower the pressure is, the further apart each molecule can be in that space. As we increase the pressure, that's forcing the molecules closer together. So as we lower the pressure, the molecules can travel further apart. But also a high temperature. And that's what we get from overcoming the intermolecular attractive forces. So in general, the lower the pressure and the higher the temperature, the more any given gas will behave more ideally. All right, let's go on to assumption 4. Gas particles will collide with each other and with the walls of the container without losing any energy. And they either collide with each other, or they certainly will collide with the walls of the container. That's what's defining what their volume is. If there were no walls of the container, they would have an infinite volume because they would just keep spreading farther and farther apart because, again, under ideal behavior, there's nothing keeping them together. Under those conditions, they don't lose any energy, and that is a big assumption. The reality, as many of you probably have heard from various physics discussions, is that no collision is 100% elastic, a collision that doesn't lose energy. Instead, we have energy is transferred between the particles upon collision. So in fact, it is these collisions on the walls, this is where we get pressure from. And we'll be talking about pressure in these experiments and in these problems and in understanding ideal gas behavior. We'll also find that these collisions cause a change in the random direction of motion. And that goes counter to the first assumption that there is nothing that gets in the way of its motion. It's not going to interact with anything, a wall of a vessel or another molecule that's going to alter its course. So really there's a lot of departures to reality for this assumption, number 4. However, with this assumption of number 4, we can still get a pretty good idea of how gases behave. The final assumption has to do with the temperature of the gas. Now we'll discuss this a little bit more in lecture. You're used to seeing temperature as either degrees Fahrenheit or in degrees Celsius, and those are all relative scales. They're relative to some constant that is arbitrarily defined. In the case of degrees Celsius, it's defined as the freezing point and the boiling point of water, whereas the Kelvin scale, which is what we're going to use, is directly related to the kinetic energy of the molecules. Or you can think of this as particle speed. And when we talk about how a gas might behave ideally, especially with respect to altering the volume or the pressure or how many moles of gas molecules we have, and we want to relate that to the temperature, that's really a relationship to the kinetic energy. How fast are those particles moving? As you increase the pressure, how does that change the kinetic energy of those molecules? We can't measure that in degrees Celsius, but Kelvin we can. And it's not degrees Kelvin, it's just Kelvin. And capital K is the letter that we'll use for our temperature, for Kelvin. And we will talk about that a little bit more in lecture. But now you have an idea of the basic assumptions of the kinetic molecular theory of gases that we use to model how an ideal gas would behave, with the knowledge that no gases will ever behave completely ideally. And I've highlighted for you a couple of places where we really do depart from reality. And we can also understand now how gases might behave more or less ideally depending on how we change some of these parameters. Yeah. Usually when you take a chemistry class, whether it's in high school or an intro class, gas laws are one of the things that you talk about. It's fairly straightforward. The math is really easy. It's just simple ratios. So we are going to do some math, but they're all simple ratios, but we're also just going to talk about how we think these things should behave, right, and why we make these assumptions. So let's just talk a little bit about temperature to begin with, all right? Now, you all probably still use degrees Fahrenheit for temperature. How many of you think in degrees Fahrenheit? Yeah, that's unfortunate. I do too. The rest of the planet uses metric system. We're not going to use Fahrenheit at all in this class, okay? So let's just forget about it. We're going to use degrees Celsius, which is what we've been doing in the laboratory, but we're also going to be using Kelvin, which is capital K. Now that's not degrees Kelvin. Kelvin is an absolute scale. Celsius is a relative scale. With What's it relative to?
Water. What about water?
Water, boiling point of water.
And freezing.
And what? And freezing point of water. That's right. It's relative to the freezing point, FP, which is 0 degrees Celsius, and the boiling point, which is 100 degrees Celsius, of H2O. Now that's relative. We could have chosen anything. The Fahrenheit scale, which I don't want to talk about, but the Fahrenheit scale is older. It shows something else for its relative measures of where we are on the scale. Celsius makes a lot more sense in several ways, but it is relative, right? So when we talk about how temperature affects gas behavior, what we're really talking about is kinetic energy of the system. All right? If I were to take a container, let's make a container here of gas molecules. All right? So each little dot here is a gas particle. Doesn't matter what the gas is. We're going to assume that this gas behaves ideally. And if we look at the kinetic energy of these molecules, they're not all at the same kinetic energy. There's a distribution. Some of them are moving a little bit, some of them are moving a lot, and they're moving in all sorts of different directions. Such that we can actually make a distribution. This is a Maxwell-Boltzmann distribution, where we look at the relative speeds, or the different speeds, or kinetic energies of these molecules in this collection. It doesn't really matter what these are. I'm not going to test you on all of these. That's the most probable speed. This is the root mean square speed. And again, it doesn't matter, the average speed. Although all of these are in part of this distribution. And it's the root mean square. And again, I don't want to write this down because you're going to think that it's important if I write it down. But I'm going to write it down anyway. The root mean square in this distribution, that's basically going to be the sum of all of the speeds squared divided by the number of molecules that we're looking at, and then it's the square of all that. Don't worry, we're not doing this, okay? But I'm just showing you different ways that you can talk about this distribution of kinetic energies in this system, okay, that actually gives us the average kinetic energy. And that's what we're going to be measuring in Kelvin. Okay? That's going to be our average kinetic energy. Now, relative versus absolute, right? That's what I want to talk to you about right now. Because when we start looking at when we increase the kinetic energy of a system, we want to see how that's going to affect the pressure and the volume of that system, given that we have some number of moles in that system. So to do that, we want to see what the actual kinetic energy of the system is, not what the relative temperature is. And the way we can think about that is in this example down here. This comes from your textbook. Let's interpret this graph here for a moment. Here we have temperature on the x-axis. There's two scales, degrees Celsius and Kelvin. And then we have volume of the system. And we have some number of particles. So here I have a system. Here's a syringe, okay? And if I pull up the syringe, I'm pulling up some gas molecules in the syringe, right? Here, let's put a medium weight here. And then I'm going to close this off. So this is now what we call a closed system. Nothing gets in, nothing gets out. I have some number of gas particles trapped in here. Let's assume that these are all behaving ideally, okay? And it's at some temperature, right? Presumably it's the same temperature that we have here in the classroom. If I start lowering the temperature in this classroom, or lowering the temperature more specifically, lowering the temperature of the gas that's inside this tube. What do you think, just on your own, I mean, just empirically, what do you think will happen to this syringe? Will it get smaller or will it get larger if I decrease the temperature that's inside of these molecules? Right. Smaller, right? Because we're lowering the temperature. If you look at this picture, right, the little red arrows, even though there's a distribution of those red arrows, if we're lowering the temperature, we're lowering the kinetic energy of the system, so those little red arrows get smaller and smaller. What that means is that, now we haven't talked about pressure yet, but the pressure is what happens when those particles hit the sides of the vessel. So if we think about that, let's say we get it really cold. That's going to get smaller and smaller and smaller. The volume gets smaller as the kinetic energy gets lower, right? Can I get it so low that the volume goes completely away? In theory, right? That's essentially what this graph is showing. This graph is showing if we take at a given pressure, so let's not change the pressure, but let's just keep it at some pressure. And then as we lower the temperature, we're lowering the volume. So we can make these measurements. And then we just do a linear regression, find a straight line, and we can show that there is a linear relationship between the temperature and the volume. Now, can we get all the way down to a volume of 0? That's what this graph is suggesting. If we could get down to a 0 volume, what do you suppose the kinetic energy would be? It would be 0. If we can get to 0 volume, that means the kinetic energy would be 0 as well. Here, let's make sure that's 0. That's what we call absolute 0. Now, that's in theory. There's lots of real reasons that it's impossible to get all the way to absolute 0. We don't need to discuss them here. If you're interested, come by office hours and we'll have a cup of coffee and we can chat about it. But this is the idea, right? It's based strictly on the kinetic energy, and if we can get the kinetic energy to be completely 0, then the volume should be 0 as well. And so we can, of course, we can't measure that, right? That's way too cold. And like I said, there's lots of reasons where you actually can't get it down to 0. But if you could, we could extrapolate what would that temperature be? Because we have these values here that we can measure. So you extrapolate down, that's what the dashed line is, to where would it hit the temperature axis, the x-axis. And then we do the same thing with the system at a different pressure. Sorry, this is pressure 2. And then we do the same thing at a third pressure. If you do those experiments carefully enough, you'll find that they extrapolate all down to the same point. And that temperature that they extrapolate down to is negative 273 degrees Celsius. Now, if you really want to be persnickety about it, it's 273.15 degrees Celsius. But in this class, we'll just work with minus 273. This is going to be what our absolute 0 would be if we could actually reach it, based on an experiment just like this. Now, the Kelvin is what we're calling, that's our absolute temperature. It's really the kinetic energy of the system. In fact, it's the average kinetic energy of the system. Okay? So minus 273 degrees Celsius, that's going to be equal to 0 Kelvin. And it's not degrees Kelvin, because degrees means that it's relative to some arbitrary standard. Kelvin is not related to an arbitrary standard. Kelvin is the absolute kinetic energy of the system. That's why we use Kelvin in thermodynamics, we use Kelvin in thermochemistry, and we use Kelvin in gas laws. So I'll be reminding you of this several times when we come up to a problem like this. But in the textbook, you'll almost always get a problem where the temperature is in degrees Celsius. You have to remember to convert it into Kelvin. And this is the conversion right here. So pressure is one of those things in science that I can't tell you why, but we have, I don't know, 10 or more different units that we use to measure pressure. And they're all used under different circumstances. We try to use atmosphere for our standard atmospheric pressure, okay? And the problems that I assign to you, hopefully are all in atmosphere, so you should never have to go through this conversion. But for example, in lab, the tire gauges that we use, those are measured in either kilopascals or in pounds per square inch. And so we just had you use pounds per square inch in the lab. But there's conversion factors. We can all go through them, but we're not going to. All right, we're going to stay working in atmosphere. Now, just to give you an idea of where this comes from, millimeters of mercury, that's probably the other one that you're most familiar with. So let me just talk about that a little bit, because that comes from a barometer, which is shown, which is shown here. Measures the barometric pressure, the pressure in the atmosphere. And we have a little rod inserted into a pool of mercury. And that rod has little markings on it. Okay. And those markings are millimeters. And it's open at the bottom and it's closed at the top. Okay. And you've got a vacuum in here. But the rest of the pool is open to the atmosphere. So whatever that atmospheric pressure is that's pushing on the surface of the mercury, it's going to force that mercury up into the rod. And it's going to rise a certain distance before it's counterbalanced by the vacuum that's at the top of the tube. And the greater the pressure is in the atmosphere, the higher that mercury is going to rise in the tube before it's counterbalanced by the pressure, and vice versa. If the pressure outside gets lower, then the column drops. So our standard pressure at sea level, this is how it's defined. The pressure of the atmosphere, just the mass of the air particles, the gas particles, being pulled down by the force of gravity, okay, at sea level, that is a pressure. Pressure is force per unit area. Force per unit area. That's pressure, okay? So the pressure of the atmosphere down on the surface, okay? So on the surface of this, it pushes it up. We define that as 760 millimeters of mercury, because that's how high the column of mercury travels in that column. So that's how a barometer works. The pressure itself, all right, it's force per unit area, but as we measure pressure in our systems, right, the pressure, the gas pressure in particular, all right, gas pressure, this results from, remember, the molecules are in motion. We have kinetic energy. Those particles are going to hit that surface with a particular amount of force per unit area. So the pressure in your system results from the kinetic motion of the gas particles. All right, so this results from the force of molecules hitting the walls of the vessel that it's contained in. Now, when we have a collection of gases, they all combine. They each have their own components of gas pressure. The perfect example of this is the air that we're breathing right now, right? The atmospheric pressure. So if I were to write the pressure of what the overall total air is, it's going to be additive of all of the individual contributions of all the gases that are present in air. So what gases do we have in air? Oxygen, what else? Nitrogen, what else? CO2 is in there, carbon dioxide. Now, if we had time, I would tell you a lot more about carbon dioxide levels in the atmosphere. Who knows, maybe there'll still be time next week, but I doubt it. There's one more that you didn't mention, but you probably don't know, and that's argon, okay? Which one's the most abundant? Nitrogen is the most abundant. And this is a solution, it's just a gas solution. So we can add all these up. We can
take the pressure of nitrogen, which happens to be around 78%. That's the composition, thereabouts. Plus the pressure that comes from oxygen gas, that's the next most abundant, that's present at about 21%. Plus the pressure that comes from argon, that's present at about 1%. And then there's a whole bunch of other ones that are present at much, much less than 1%. I'll just put one up here because we care about it, carbon dioxide. Right? But carbon dioxide, this is present at much, much less than 1%. Because you notice that 78, 21, and 1, they add up to just about 100%. Okay. So those are the three main components. So if we measure at standard conditions, so at sea level, right, we have standard atmospheric pressure, that's going to be 1 atmosphere. So if this is 1 atmosphere, then we can talk about what's called the partial pressures. Partial pressure is just those, the individual components coming from each gas. So the partial pressure of nitrogen in the atmosphere at sea level would be 0.78 atmosphere. For oxygen, it's 0.21 atmosphere. For argon, it's 0.01 atmosphere. And for all the others, it's a whole lot less than that. All right, so this is what Dalton's law of partial pressure tells us. It's a very simple law. It's just that the total gas pressure of your mixture is just going to be the sum of the partial pressures. There's nothing magical about partial pressure. It just sounds confusing, perhaps. It's just the individual contribution. So let's now talk about the concept of ideal gas and talk about the ideal gas law. I like teaching this in reverse order of how textbooks usually introduce it. Textbooks usually introduce this from a historical point of view, talking about the individual experiments that culminated in the ideal gas law. And I'm going to start with the ideal gas law and work our way backwards. So many of you are already familiar with PV equals nRT. Who's never heard of this before? I should say, who's heard of this before? Right, everyone's heard of PV equals nRT. I like to call it PIV nerd. Of course, that's not how it's spelled, but it gets the idea across. PIV nerd. If you can remember PIV nerd, then you can solve any of these gas law problems without having to memorize what the individual relationships are. Okay, so we're going to start with PIV nerd and we're going to piece it apart and work our way backwards. Now we've got 5 components here, but one of them is a constant. Which one's the constant? R. This is our gas constant. We'll be talking about that in a moment. But the other components are the 4 variables that change relative to each other as following sort of the kinetic molecular theory of gases, those stuff that I covered on that video. So those 4 variables, so the ideal gas law, PIV nerd, this relates 4 gas variables. Pressure, which we just talked about, and we're going to be measuring pressure in atmospheres. Volume, which we're going to be measuring in liters. Then we have the number of moles of gas particles. So that's what lowercase n stands for. This is going to be moles. And then finally, T is for temperature, but we're going to be measuring the kinetic energy of these molecules. So we need to be using Kelvin, our absolute temperature. Now, if we were working our way historically, we would be looking at the experiments that looked at the individual pairwise relationships. In fact, you did one of these in lab yesterday. You did 2 of them, but the first experiment you did in lab on Tuesday was looking at the relationship between pressure and volume. Now that's what we call Boyle's law. I'm not going to have you memorize the names associated with these relationships, but I do want you to know what the relationships are. Pressure and volume. You discovered this already. They're going to be inversely proportional. As one increases, the other one decreases. And when you write that in a proportionality, you have them on the same side of the proportion. So pressure and volume As one increases, the other one decreases. And these are going to be proportional to, that's what this side word squiggle means. This is a proportionality. The number of moles and temperature. These are the relationships that we get from the historical experiments. If I were to move all this to the same side of the proportionality, I would have pressure times volume divided by the number of moles times temperature. Okay. So you can see, looking at this relationship now, how they all vary. If you change one, the others are going to readjust so that overall the values stay the same. Just like you discovered in lab. If you change the pressure, the volume is going to adjust in the opposite direction. But in that case, you're keeping the number of moles constant. You had that syringe cap, all right? So you're not changing the moles, so N is constant. And ideally, you weren't changing the temperature either. So when the number of moles is constant and temperature is constant, then the denominator there doesn't factor in, and then the relationship is just P times V. Whatever you do to the volume, the pressure is going to change appropriately so that the overall value stays the same. That's what we get from these proportionalities. Okay. So what we have then, the last thing to discuss is R, the gas constant. Okay. All R is, it's not a big mystery. This is probably the most confusing part to students when they start studying gas laws, because they remember learning about PIV-NERT in an earlier class, and you're just given that equation to work with, and perhaps there wasn't a long discussion about it. All R is this relationship defined under standard conditions. Okay, because as I just said, if you know this relationship, if you change one variable, the other three are going to change such that it's always equal to a constant. Now that's assuming that we've got an otherwise what we call a closed system. And in a closed system, we're not letting materials in or out, okay? So is that concept straightforward? We got the four things, they're all related to each other in this way. You change one, the other three are going to readjust so that, because they can't go anywhere. The molecules, the gas molecules can't go anywhere in a closed system. So if you change one variable, the other three are going to compensate so that overall this proportion, or now that I've written it on the same side, right, this equation will always equal the same value. It's a constant. So I'm just going to define what those four variables are under standard conditions. So R, this is standard conditions. And two of them we refer to as standard temperature and pressure, or STP. Standard temperature is going to be 0 degrees Celsius. But since we need to work in Kelvin, what is that in Kelvin? It's 273 Kelvin. Standard pressure is going to be our standard pressure 1 atmosphere. And we're going to do this for 1 mole of gas. So at STP, we can measure this. 1 mole of any gas particle that's behaving ideally, and let's just assume that's all of them. But if you watched the video, you know that there's a lot of assumptions in that. No gas actually behaves ideally. And for those of you who go on to Gen Chem 2, you'll be learning about some more details about how these things can behave less ideally than others. But for now, we're assuming that everything's ideal. That makes this model work perfectly. And by the way, most of our assumptions are perfectly fine when you're measuring gases under general laboratory conditions. So at STP, 1 mole of gas, we can measure this, will occupy 22.4 liters volume. Okay? So we can now set up that proportion. So R is going to be equal to, pressure is 1 atmosphere. The volume is 22.4 liters. the number of moles is 1 mole, and the temperature is 273 Kelvin. And when you add all that up in your calculator, you get the value of the gas constant, which is 0.0821. And the units, nothing cancels out here. So the units are liter atmosphere divided by mole Kelvin. And we can use that in our equation now, because we know what the proportionality is here. Pressure volume product is proportional to the mole temperature product. And doing this sets them equal to our constant, which is R. Okay, so if I can rearrange that back, that gives me Pivnert. The only reason R is defined this way, I mean, you can define R any way you want mathematically, as long as it goes into this equation the right way. We're defining R this way because we're using PV equals nRT. And frankly, the best reason I can come up with for putting R here, not somewhere else, is that it spells Pivnert. And you can remember Pivnert real easy, okay? But that's where R comes from. So you can now always rederive, if you needed to, what R is. The only thing you really need to remember is that at standard temp, well, I guess you need to remember what standard temperature and pressure are. So remember that, all right? 0 degrees Celsius or 273 Kelvin in 1 atmosphere. For that, 1 mole of gas will occupy 22.4 liters. If you can remember Pivnert and rearrange things like this, you'll be able to then remind yourself of what all the individual relationships are just by going back to Pivnert. And that kind of looks like this. I made a whole slide here for you. Right, so the top part I just did, it's defining R. Now, by the way, for those of you who have taken other classes where you use a different value for R, has anyone done that? Use like 8.314 for R? Nobody? You'll experience that later on. It's still the same R. The only difference is the units. You've done a unit conversion for the pressure. In this R is for pressure at 1 atmosphere. There are other R's where maybe you're doing it in kilopascals, or there's other R's where we've done other conversions to turn it into joules. That's work as well. So I'm just telling you, you may find other numerical values for R, but it's the same R. It's just the units are different. Okay, so when you study this individually, we study these as Boyle's law, Charles's law, Avogadro's law, etc. We'll be looking at those relationships. And I may be using those names, but I'm not going to be testing you on the names, okay? I'll be testing you on knowing the relationships. So really, all we have here is condition 1 versus condition 2. I've just taken that same relationship here, and as I've already mentioned, if you change one of those 4 variables, or even 2, or even 3 of them in a closed system, everything is going to rearrange itself so that the individual values may be different, but the product will be the same, a constant. So the only reason R is a constant here is because it's constantly defined by the same conditions. Those don't change. All right. So I can put a stop it. I don't want that. I can put a 4th condition here, or a 3rd condition, R. And here's the PV equals nRT for R. So let's call this condition R. And then as I change the conditions from R, I'll be able to figure out what those values are if they're unknown, because I can just set it equal to the conditions that are standard in R. That's why it's a constant, but it's an artificially derived constant. All right, so if you need to remember what Boyle's law is, and I haven't told you what it is yet, okay, but we can just go ahead and look at it, right? Boyle's law looks at the relationship between pressure and volume. That's going to be when the number of moles and the temperature are constant. This is the one that you did in lab on Tuesday. So we already talked about this one. These are going to be inversely proportional. That's what you measured experimentally. You found that when pressure and volume, if you multiply them together, you'll always get the same value. As the pressure increases, the volume decreases, and vice versa. So that means that if we have these together, they'll always equal the same value. That's the same as, let's go over here. Let's look at condition 1 and condition 2. Pressure and volume are changing. Moles and temperature are not changing. So these are constant. These never factor in. So look what we have. PV in condition 1 is equal to PV in condition 2. See how that works? So PV in condition 1 is equal to PV in condition 2. That's what this is telling us. Now, if I were to work this back as a proportion, we need to separate. How does pressure vary with volume? That would be the pressure is proportional to 1 over the volume, because now I'm moving them to the opposite sides of the proportionality. That's why it's called an inverse relationship. These are inversely proportional. Okay, Charles's law, that's what you use to approximate what absolute zero was in your lab exercise. So we know that the relationship, this is a direct relationship. So if I write that as a proportionality, that means that the volume is directly proportional to the temperature. If I move them to the same side of the proportionality, then whatever the pressure and volume is in condition 1 will be equal to the pressure divided by the volume in condition 2 in a closed system. Right, so that's going to be the same as this. Pressure divided by temperature in condition 1 will be equal to the pressure divided by the temperature in condition 2. Now, of course, this is when the other two variables are held constant. So in this case, that's going to be moles and pressure. Now, how are you going to remember that it's volume divided by temperature? You're going to go and you're going to remember Pivnert, right? And with Pivnert, you write it out. PV. If you can't remember this, just PV equals nRT. You want to know what the relationships of pressure, volume, and moles and temperature are. You start with this and you rearrange it to PV divided by NT equals R. And you can solve anything, any of these relationships. So there you go. On the right-hand side, we're looking now at the relationship between volume and temperature. When pressure and moles are held constant, it's volume divided by temperature in condition 1 is equal to V divided by T in condition 2. Avogadro's law is looking at the relationship between moles and volume. Let's just get it from Pivnert, okay? When moles and volume are changing, this is going to be then when temperature and pressure are constant. So what's the relationship? Moles and volume. That's what's changing. So are they directly proportional or inversely proportional? That one's a little bit of a logic. You got to do it in your head, right? It's going to be direct, right? Because this relationship, V divided by N in condition 1 is equal to V divided by N in condition 2. That's the equality. So to turn that into proportionality, they're going to be on opposite sides of the proportionality. So that's a directly proportional. As one, and direct also means as one goes up, the other one's going to go up. As one goes down, the other one's going to go down. Whereas when they're inversely proportional, like pressure and volume, when one goes up, the other one goes down to compensate, such that again, between condition 1 and condition 2, you have the same overall value, product, I should say. So these are directly proportional. And so on and so forth. I don't think I need to derive all the rest of it. Okay, I think you get the point. If you remember Pivnert, you can rederive any of these relationships. And then the rest of it, honestly, is just ratios. These are all simple ratios. Everything that I've written here, right? This is a ratio. This is a ratio. This is a ratio. Solve for X. All of these problems have only one unknown and the rest are known, and you just rearrange to solve for the unknown. But you also have some problems where you're working with PivNert directly. It's a more simplified way of working with the ratio because we're converting everything that's R into that one number, that 0.0821. Okay, so let's work a few problems with that and I'll show you what I'm talking about. So here's one from the textbook. We're going to calculate the number of moles of nitrogen gas in a 3-liter balloon at 27 degrees Celsius and 0.95 atmospheres of pressure. We want to know the math. Well, first we want the number of moles and then we're going to work on the maths. But let's just do the top part. So we've got moles. This is what we want to calculate. So moles, that's going to be our question mark, our variable. Our volume is 3 liters. What's our temperature in Kelvin? 273 plus 27 is 300. You got to make sure, probably the single most prevalent mistake that students make when they're working a gas law problem like this is they're given the data in Celsius and they don't convert it to Kelvin. All right, and then here we have our pressure. We've got everything that we need. If we just plug this into PivNert, because we know what R is, right? R is the gas constant. So let's just take PivNert and solve for N, and then it's just algebra. N is equal to PV divided by RT. And we know all this. So the pressure is 0.95 atmosphere. The volume is 3 liters. I'm going to put temperature first so that I can show you where the units of the gas constant go. So the temperature here is 300 Kelvin. And then the gas constant, which is 0.0821. Now the units are liter atmosphere per mole Kelvin. Okay, but this is in the denominator. So I'm going to put the mole Kelvin. Now that flips up to the numerator. And again, that's just algebra. So let me then just show you that the units all cancel. Kelvin cancels with Kelvin. Moles cancels with, no, we don't want moles canceling. That's what we're calculating. Moles don't cancel with anything. Liters cancels with liters, atmospheres with atmospheres, and we're left with the units of moles in the numerator, which is what we're trying to calculate. So all I'm doing here is how you would probably be solving this problem if you're working it in SmartWorks or if you're challenged with this on an exam. You're given 3 of the 4 variables and you want to solve for the 4th one. So you're going to use PivNert because PivNert has embedded in it R, and R, as I've just explained, are those 4 variables under a set standard condition. So it's really no different from what we were doing right up here, setting condition 1 to condition 2 and solving for the unknown. Except now, instead of condition 1, we're using condition R, and it's all embedded. So let me show you that. But first, let's get the numerical answer. This is equal to, I got 0.12 moles of N2. Now, this idea of an ideal gas, N2 may not be an absolute ideal gas, all right? But if we use those assumptions of ideal gas behavior, then we would have 0.12 moles of any gas under these conditions. It doesn't have to be N2. This number, 0.12, it's independent of the identity of the gas. It's independent of the gas identity, meaning it could have been, it could be O2 gas, it could be CO2 gas, it could be methane gas, it could be anything, because we're only looking at moles. The number of moles of the gas is independent. That number won't change. Now, in this case, though, we're asked what's the mass of the gas, then you have to know what the identity is. For us to be able to answer this question here, we would take the moles, 0.12 moles of gas, and we would then use what? The molar mass of N2, which is, it's about 28, right? Because nitrogen's 14, 14.01. So it'll be 28.02. You good with that? And where does it go? In the numerator or the denominator? The denominator. No, it goes in the numerator. Because moles, we want the units to cancel out. So we're going to have our 28.02 grams of N2 per 1 mole. And that would give you the number of grams. Okay? But let's go back to Pivner and let me show you that it's really no different from the ratio. This is the exact same thing as if I were to do the problem this way. Let's just look at R, and we're going to set our condition R to our conditions in this problem. So R is 1 atmosphere and 22.4 liters divided by 1 mole at 273 Kelvin, right? That's R. And we're going to set R equal to our 4 conditions, of which we have 1 unknown. Let's put them in. Our 4 conditions here are 0.95 atmosphere. The volume is 3 liters. N is our unknown. And the temperature is 300 K. And I challenge you to use your calculator the right way. If you solve for N, you'll get 0.12, because everything that's on the left-hand side here that I've labeled R, that's your 0.0821. This is 0.0821 liter atmosphere per mole Kelvin. Okay. What I've written here in blue on the right is no different from Pivner. It's R equals to PV divided by NT. Okay. So it's just showing you the long way of why you can just plug things into Pivner and it works. Now let's do another one. Bottles of compressed oxygen carried by climbers ascending Mount Everest contain 1 kilogram of gas. What volume of oxygen can 1 bottle deliver to a climber at an altitude where the temperature is 0 degrees Celsius? There's a lot embedded in these word problems. So rather than having you figure that out, I'll just piece everything out here for you, okay? So we've got a mass of gas and it's oxygen gas. So we need to get all of that into moles. Because for us to work with gas laws, they're independent of the identity. So let's just get this into moles. And we can do that, right? That's something you can do. Figure out how many moles of oxygen gas that is. How would you do it? Dimensional analysis, right? Let's start with just one thing and work our way there. 1 kilogram of O2. Let's get that into grams. How many grams are in a kilogram? 1,000. So we got kilograms in the denominator. So 1,000 grams per 1 kilogram. And the molar mass of oxygen gas, 31.998, right? That goes down here. Grams of O2 per 1 mole. And that gives you 31.25 moles of O2. That's N for our problem. What about temperature? What's temperature? 273. What's the pressure? 0.35 atmosphere. And what are we missing? Volume, but that's what we're asked to calculate. What's the volume? So that's our unknown. Okay, so now we can solve this. We need to rearrange Pivner to solve for volume. All right, let's do it. PV equals nRT. Solving for volume is equal to nRT divided by pressure. We know all of those values. number of moles. We just calculated that. That's 31.25 moles. Now it could be moles of anything, but we know that this is moles of O2 that we're calculating. Here's our gas constant, 0.0821 liter atmosphere per mole Kelvin. And then we've got temperature, 273 Kelvin, divided by the pressure, which is 0.35 atmosphere. Let's make sure our units cancel out. Moles with moles, Kelvin with Kelvin, atmosphere with atmosphere. And we're left with the units that we want in the numerator, which is good, because if you're trying to calculate for volume, but your units are in the denominator, then you've done something wrong, right? You've calculated the reciprocal, most likely. All right, so you do that math. And when I did it, I got a nice round 2,000 liters of oxygen gas. All right, so this is at 0.35 atmospheres. This is at the top of the mountain, okay? At 0.35 atmosphere. That's for 31.25 moles. This distills down to 2,000 divided by 31.25 is about 64. So this is about 64 liters for every 1 mole. Okay, again, that's going to be at 0.35 atmospheres. If we come back down to sea level, okay, or at standard temperature and pressure, let's take a look at what volume that same number of moles of gas occupy. Because we know that at standard temperature and pressure, which is what again? 273 Kelvin and 1 atmosphere. Okay, under those standard conditions, what's the volume of 1 mole of gas? 22.4, right? There's 22.4 liters per 1 mole, but we're still working with 31.25 moles. Okay, but look at this number, right? At the top of the mountain, we had 64 liters per 1 mole. At standard temperature and pressure, it's only 22.4 liters per mole. So the same number of moles is going to occupy a much smaller volume, right? If you multiply these together, you get only 700 liters of O2. But there's a relationship here. Pressure and volume, right? Let's put that in green. Here's pressure 1. And at that pressure 1, we have this volume 1. At pressure 2, 1 atmosphere, we have this volume, V2. And what's the relationship between pressure and volume? PV in condition 1 equals PV in condition 2, right? So let's make sure that that's right. So P1 is 0.35 atmospheres. Here, let's keep the units in here. Atmosphere times 2,000 liters. Is that equal to 1 atmosphere and 700 liters? Is it? Somebody whip a calculator out. It is. Yes. And it should be, because all I'm showing you in this example is this relationship. Now we're just focusing on pressure and volume.